Have you ever looked at a football shot map and thought, hey, that looks kind of like a constellation? Well, my friend John did. John thought that this shot map, the screenshot is from the Infogol app. He thought that this shot map looked kind of like this constellation, the Seven Sisters. As an aside, you might be wondering why the Seven Sisters constellation only has 6 visible stars. And it turns out the answer involves some really interesting history and folklore, which I won't get into here, but I recommend looking up. Anyway, John tweeted about this, and it got me wondering, what if we could find a shot map for every constellation in the night sky? So not just the Seven Sisters. What if we could find one for Orion and the Big Dipper and lots of other constellations who I don't know the name of because I live in a very light polluted area and can't really see the constellations. But what if we could look them up and find them? Maybe that would be fun. So this is what I'm going to talk about. So when I talk about constellations, I'm specifically going to talk about the Western European canon, just because being from the United Kingdom, these are the ones that I see and have come across. But other ones do exist. You could redo this project for a different canon, a different set of constellations, which maybe would be interesting too. I also just want to clarify specifically when I'm talking about shot map here, I'm going to talk about all of the shots from a single match, from a single team. Finally, the data that I'm using is Stats Perform event data. For every event on the pitch, every pass, shot, tackle, they give the position of that event and the type of that event as XY coordinates on the pitch. So for this, I'm just looking at shots, but it's Stats Perform data. To compare shots and stars, we need to put them onto the same terms. We need to make them comparable. So let's quickly go over the format that the data comes in. So for shots, I mentioned that they come in XY coordinates. So essentially you get something that looks like a spreadsheet or that can easily be modified to look like a spreadsheet, which has for each shot one row, and that row will say who the player that took the shot was, what team they were playing for, what match they were playing in, and like I said, the X and Y coordinates on the pitch of the shot. The X coordinate is how far up the pitch towards the goal that the event is, and the Y coordinate is how far to the left or to the right the coordinate is, and both of these go from 0 to 100. But the coordinates of stars are not given like that. So the way that star coordinates are given is they're given in terms of where they are on the surface of the sky. So if you imagine us on the Earth looking out at the night sky, the night sky can be thought of as a sphere around the Earth, and the stars appear as points on that sphere. Now, obviously, in reality, those points are in space, varying distances away, but the way that we observe them is very similar to if we're looking at as a sphere around the Earth. So the way that star coordinates are given is as points on the sphere, and they're given in the form of 2 numbers. The first is right ascension, which is essentially like longitude on a globe, and it's just how far around the equator they appear. And the second is declination, which is how far up towards the pole they appear. This coordinate system is useful when you're talking about stars because it accurately describes how we perceive the stars. And as the Earth rotates and shifts on its axis, depending on the seasons and the days, the position of the stars will move relative to the surface of the Earth. So this coordinate system is very useful for describing that. However, we're not interested in astronomy here. We're interested in something far, far stupider. So we want to go from this right ascension and declination into simple 2D coordinates, into x, y, coordinates on a plane, which we need to do. Somehow we need to get these coordinates into flat xy coordinates. So to go from coordinates on a sphere to coordinates on a plane, we need to talk about projections. You might be familiar with projections from thinking about the globe and how we get a flat map of the Earth when the Earth itself is roughly a sphere. So commonly for the Earth we use the Mercator projection. The Mercator projection is popular because it's very useful for navigation, because of the way that it preserves shapes and directions and the way that north and south are consistent across the whole map. But the needs of navigators and sailors are quite different from our needs. What we want to do is we want to preserve the shape of each constellation as it appears to a person looking at it from the surface of the Earth. There's also an additional feature in that we don't actually care about projecting the whole night sky. We just want to look at one constellation at a time. We want the XY coordinates of each constellation, but those coordinates don't have to be consistent across all of the different constellations. So, what is the projection that we use? So let's just think about how we might do it for one constellation. And for this constellation, we want to go from right ascension and declination to x and y coordinates. So imagine this constellation on the left-hand side. We want to recreate how it would look to someone standing on the surface of the Earth in xy coordinates. So we need a projection that will do this transformation for us. The projection that I use for this is called the orthographic projection. Sometimes it's called the planar projection. To apply this projection to each constellation, I first took the midpoint of the stars in that constellation. Then, imagine placing a flat plane onto the sphere so that it touches the sphere exactly at that midpoint and only at that midpoint. If you're familiar with a tangent to a circle from geometry, this is the same thing, but in 3D. Then, for each star, you take a line and you start this line at the Earth, so the center of the big sphere, and you pull this line out to the star on the surface of the sphere. And then, keeping that line the same, you keep extending it through the sphere until it touches the plane. The point where that line, which goes from the Earth through the star, touches the plane is the projected point of the star on the plane. So then, getting the xy coordinates of each star in the constellation is simply a matter of reading off their location on this plane. And because the plane is a 2D surface, we can get those xy coordinates no problem. So this is how the orthographic projection works. Now, fortunately, we don't need to build physical models of these things. We can just do this with maths. But this is essentially how it works. So now we have shot maps in terms of x and y coordinates, and we also have constellations in terms of x and y coordinates. The question then becomes, how do we match a constellation to a shot map? How do we find the best shot map for each constellation? The database I was using for this project has about 60,000 games in it, so 120,000 shot maps, which is a lot to compare to. So the first step I took was to filter out any shot maps where the number of shots wasn't the same as the number of stars. I don't think this is 100% necessary. I think there are ways you could try and handle extra shots or missing shots, but that added some extra complexity that I wasn't really happy with, so I've ignored that for now. Once we have this subset of shot maps, where all of them have the same number of shots as we have stars, we need to find the shot map which looks the most similar to our constellation. If at this point you think this sounds like that meme, draw the rest of the owl, then you're right. We need to break this down a little bit more. What do we mean when we say the most similar shot map? Well, to find the most similar one, we need to find some way of ranking, of ordering all of the shot maps. So to order each of the shot maps, we want a number that represents how similar that shot map is to the constellation. Let's call this a similarity score. If we have a similarity score for each shot map, we can just order them and find the one with the highest similarity score. But we still need to draw the rest of the owl. What is the similarity score? How do we calculate the similarity score? Let's just look at calculating the similarity score for one shot map. If we think about how we might do this visually, we might take the constellation and overlay it onto the shot map and see how close are the two images. How closely do the shots line up to the stars in the constellation? But we can do more than this. When we think about a shot map looking similar to a constellation, we're pretty happy for the constellation to rotate or move around. So overlaying the constellation onto the shot map isn't enough. We also need to account for stretching it, moving it around on the shot map, and also rotating it. And we want to find the combination of these things, the combination of translation, rotation, and scaling that makes the point of each shot closest to its nearest star. The way I imagine this is that I'm attaching rubber bands between each pair of one constellation star and one shot, and doing this for all of the pairs of stars and shots, and then letting go and letting it find the place which is like the best orientation, such that those rubber bands are stretched the least. We want each of those distances, those rubber bands, to be as small as possible. And we're just finding the combination of transformations that makes that happen. There is one problem with this intuition, with this intuitive explanation of the rubber bands, which is that if, for example, you rotated the constellation 180 degrees, those rubber bands would be really stretched. And in fact, the nearest point, the nearest shot for each star would be totally different to the one you started out with. So this method of using the rubber bands kind of requires you to know in advance which shot and which star are being matched. So this is a problem with the intuition, but we can fix that with maths. We can express this problem mathematically using a section of mathematics called linear programming. Linear programming is this amazing bit of knowledge where once you know about it, once you've learned a bit about it, you have this incredibly high leverage tool that can make problems that otherwise look really nasty way, way, way easier. I really recommend looking at it and learning a bit about it. The way it works in this problem is we calculate the distance between all possible pairs of stars and shots for each transformation. Then linear programming will tell us which mapping of stars and shots gives us the lowest overall distance. So for a given set of transformations, linear programming tells us which star and which shot should go together, where we should put the rubber band. We can take this function and put it into another optimizer that will iterate through combinations of transformations, so translation, rotation, and scaling, to find the set of transformations with the lowest overall distance. So linear programming tells us the mapping of stars to shots for a given transformation and the distance with those mappings. And then this other optimizer finds the set of transformations that minimize that distance. This final distance, after we've optimized the transformations and the mapping, is our similarity score. And as we said earlier, doing this for every shot map and every constellation lets us find the right shot map for each one. So what do the results look like? Some I think are quite good. Others are not so good, I think. But overall, my favorite has to be the algorithm matching Lupus to a Wolfsburg shot map. If you want to find out more, I've posted all the results for every constellation online, and I've put the code and data on GitHub if you want to remix or run the project yourself. The links to both of those will be in the description.